So we're going to do here all the homework questions for the KSP and thus complete the unit almost. We still have, I'm still going to do, I think, a couple more questions with the pH and equivalents, just so that we get like a good understanding of how to do those questions. But this will be the last almost video of one compound that becomes less soluble at higher temperatures is calcium carbonate. It's interesting. I did not know that. Well, fun fact right there. Okay, so this is the homework on page 432. Write a balanced chemical equation that represents the dissociation of this in water. So I'm hoping we're all like reasonably okay with writing balanced equations. Cu copper chloride is CuCl. Whoops, that looks like Cua. Solid plus water gives Cu plus Cl minus. So the KSB expression is Cu plus times Cl minus. That's it. No solid because we don't consider solids. These two we know are aqueous. Barium fluoride. So my KSP expression is going to look like fluoride concentration squared times the barium concentration. There, that wasn't too bad. You just got to keep a watch out for these squares that pop up here and then. And this is obviously equilibrium concentrations of both these ions. Silver sulfate, Ag2SO4, 2Ag plus SO4 2 minus. So my KSP is going to be equal to Ag plus squared SO4 2 minus concentration. Similarly, calcium phosphate looks like this. And again, I'm assuming that you're good with crisscross method and writing ions. We practiced this a whole bunch in grade 10 and 11. So all these are aqueous ions. All ions are aqueous. I'm not going to write that. But so the KSB expression here would be calcium 2 plus cubed, phosphate 3 minus squared. Ag2CO3, same thing, 2Ag plus, CO3 2 minus, KSB is Ag plus squared, CO3 2 minus. Magnesium ammonium phosphate. That's interesting. I don't even know what this answer is. But presumably, this guy is going to break up into magnesium, ammonium, and phosphate, which then gives my KSB just the product of those three things, but no powers because all of them are there. Okay, nitrate has a very low solubility. So iron nitrate, write the KSB expression. So I'm going to skip the equation step and just go directly to iron 3 plus times nitrate cubed. Do you expect the KSB to be larger or smaller than aluminum hydroxide, which has a slightly higher solubility? So aluminum hydroxide has higher solubility, and therefore it also has a higher KSP value, and therefore, so I expect the KSP of iron nitrate to be smaller than the KSP for aluminum hydroxide, because I say aluminum hydroxide has a higher KSP. Okay, what's next? This stuff. Okay, solubility of silver cyanide is given, calculate KSP. We have done this question already in our notes, I'm pretty sure, somewhere in the old video. Is this still here? Yeah, this question. So we did, oh, I erased it, the problems. Well, I'm sure you know how to do that question. Basically, you set up an equation where you have x equal, so again, I've given maximum solubility, so x equals 1.5 times 10 to the negative 8. And if I do my ICE table, I get KSP equals x squared, which then equals 2.25 times 10 to the power negative 16. So that's my KSP value. Okay, saturated solution of copper 2 phosphate has a concentration of that many grams per 100 milliliters of solution. What is KSP? So this is exactly the same thing. So again, maximum solubility, saturated solution. I'm giving you in various forms the solubility of the salt. When I say me, I say the textbook. Except in this case, it's a bit weird because I've given you a gram value and a milliliter value. So I had to convert that into moles per liter because I need a concentration. So first things first, we're going to find the molar mass of Cu3PO42, which happens to be copper 2 phosphate. Molecular weight is 380.58. Wonderful. So I'm going to convert my 6.1 times 10 to the power negative 7 grams, table, whatever, 1 mole per 380.58 grams. And also, so now that I have moles, I'm going to convert into concentration. So essentially I have to divide by volume, which makes 100 milliliters, which is 0.1 liters. There. So I do 6.1 times 10 to the power negative 7 divided by 380.58, also divided by 0.1. And this gives me a final concentration of Cu3PO42 of 1.603 times 10 to the power of negative 8. That's my concentration. So now I have to calculate KSP. So for that I have to write an equilibrium expression. I'd like to write out the equation here just so that we can see exactly what's going on. 3Cu 2 plus 2PO4 2 minus. Again, you do your 0, 0 plus 3x plus 2x, 3x, 2x. KSP equals 3x cubed times 2x squared. 3 cubed is 27, please, not 9. We'll remember that. And 27x cubed times 4x squared. 27 times 4 would give you 108, x to the power of 5. But we already know what our x is. It is the maximum solubility at equilibrium, solubility at saturation, maximum solubility, molar solubility. All those things mean our x value, right? So our x value was 1.6 times 10 to the power negative 8. So I'm going to raise that to the power of 5. And I'm going to multiply it by 108, which gives me a KSP value of 1.14 times 10 to the power of negative 37. Wow, that seems very weird. What salt is this? Copper phosphate? It is 1.4 times 10 to the power of negative 37. If you check the back of the textbook, that is accurate, close enough. So we'll take that. Saturated solution of calcium fluoride contains 1.2 times 10 to the power of 20 formula units of calcium fluoride per liter. Okay, let's do this where we don't have space anywhere. I'm going to do this right here. So 1.2 times 10 to the power 20 formula units of calcium fluoride. Again, I want to find my number of moles of calcium fluoride. So I do, what is this? 1.2 times 10 to the power 20. 1.2 times 10 to the power 20 formula. I can't write a short form for that. So we know that from our table we're trying to get to mole per liter, right? So we want mole on top, and we have 6.023 times 10 to the power 22 times 10 to the power 23 formula units in 1 mole. So we're gonna do that, and then we're also going to divide by, because now I have moles, I want to divide, and it says per liter, so that's really kind of unnecessary. So we just do 1.2 times 10 to the power 20 divided by 6.022 times 10 to the power 23, which gives us a concentration of 1.99 times 10 to the power negative 4. Again, this concentration is basically saturated solution. This is what is giving us our molar solubility. This is our X value, essentially, when I calculate the concentration of that. Even though, like, realistically, I'm going to ignore this more or less in my ICE table. I'm getting my X value from the concentration of this that is present. So Ca2 plus 2F minus like so. KSP equals X times 2X squared, which is 4X cubed, and X was this guy. So I take the cube of that function, multiply by 4, function I said, cube of that number, and I get 3.165 times 10 to the power of negative 11 is my KSP. Let's look that up. Fluorides, where are fluorides? Calcium fluoride, 3.45. Yeah, that's very similar to the KSP at the back of the textbook. Okay, I have a solution in parts per million. This is an interesting question. Calculate KSP, stating the assumptions that you made when you converted ppm to mole per liter. So, okay, what is the definition of parts per million? That means I have this many So the definition of parts per million, is the mass of solute in 1 million milliliters of solution. So again, we have this many grams in 10 to the power of 6 milliliters, which is 1.5 times 10 to the power negative 4 grams in 10 to the power 3 liters of solution. And I'm going to convert that into moles by doing a 1 mole times what is the molar mass of mercury 1 iodide. Molar mass of I don't know why it's Hg2I2. It's weird. And why just not HGI? But molar mass of Hg2I2 is 650, holy moly, 654.98 grams per mole. So I do 1.5 times 10 to the power negative 4 divided by 1 times 10 to the power 3 divided by 654.98 gives me a concentration in 2.29 times 10 to the power negative 10 moles per liter, and this is essentially our X. This is our concentration of this is our saturated solution, so our molar solubility. So Hg2 plus Hg2 plus. Oh, it looks weird like this. I don't know. I've never seen that before. Well, learn new things every day. So if you write the expression like so, you get 0, 0, plus x plus 2x, x, and 2x. So KSP is x times 2x squared, which is 4x cubed. But I know my x, I've already calculated that is that, so I'm going to take the cubed. That multiplied by 4, KSP turns out to be 4.805 times 10 to the power of negative 29 is my KSP. And again, technically parts per million is number of grams divided by number of grams of solute divided by number of grams of solution times 10 to the power of 6, right? So it's really a grams divided by grams. So we just made an assumption that the number of grams of solution we just made grams to milliliters because the density of water was 1 gram per milliliter. Also, we assumed that the mass of this mercury did not affect. So technically, because this is mass of solution, the mass of solution should have been 1 billion. It should have been 1 million. It should have been 1 million plus 1.5 times 10 to the power negative 4 grams, which I mean basically is that's like saying 1 million 0.000154, which is essentially 1 million. So we just make that assumption as well. So there's two assumptions. Density of water, density of a mercury iodide solution was the same as density of pure water. That's A. And assumption B is converting the mass of solution we assumed was just the mass of the solvent, water, not the complete mass of solution, which are reasonable assumptions to make. We will, I don't know, what's the next question here? I think we shall do these questions. We have this stuff. This stuff. Not doing that. We're doing that and that. Okay, we will switch over to another video for our next question, set of questions. Just because we have, or maybe we should just power through this and then do common ion effect and others in another video. Interesting. So we'll do this, we'll just split the videos up, no problem.